Okay, so my name's Doug, and I'm here in Wisconsin, which is in the northern part of the United States, and we're still pretty cold. So we're getting ready for our golf season. But the snow just melted last week, so we're looking forward to some warmer weather. But anyway, so I guess that introduction is that turf grass management is a very regional activity, as you know. And so the stories that I'm about to share are heavily influenced from where I do my research and may or may not apply exactly to where you're growing grass. But I do think that there are lots of parallels and lots of things we can learn from each other. So I'm going to talk today about soil testing and plant analysis. So let's get going here. And it is an honor to talk to you today. It's always an honor to be thought of to speak to other parts of the or other parts of the world. So I am very honored by the invitation. Okay, I'm going to start off with a quote from O.J. Knorr, who is was a golf course consultant and wrote one of the first books on turfgrass management in 1928. But he was also a soil scientist. So I'm in the Department of Soil Science here at the University of Wisconsin, and I study soils for a living, just like O.J. Knorr did. And he says that there's a tendency to place too much emphasis on the value of soil testing. This is true of technical workers as well as salesmen. These methods have a promising future, but their present usefulness is limited by imperfect methods and a lack of definite correlation with field experience. So, and that quote was from 1928, and a lot of things have changed, but I think there's a lot of wisdom still in this quote. So we're going to talk about what has changed and what remains the same from 1928. The other quote from about the same time that I like to share is from the United States Green Section. And they say it a little bit more bluntly that soil analyses, these are of practically no value. No one living can tell what they mean. Okay, so clearly in the 1920s, we didn't have strong confidence that soil testing was of much use at all. Now, I think there's a lot of confusion around soil testing because it's complicated. There are lots of different numbers with decimal points and units that are sometimes in percent, sometimes in parts per million, or the most unique one here is milliequivalents per 100 grams. So it's very intimidating, very complicated, and I think that is part of the reason that people are not really sure what a soil test is telling them. And now many soil tests will take that complicated numbers and units and use translate it by putting a bar graph here. So for organic matter, this soil test, even though the number was 9.3%, they're interpreting that as very high. Okay, and the phosphorus is very high, and the potassium is medium. So that makes understanding soil tests a little bit less intimidating. But the question that I want all of you to ask now at the end of this talk is very high according to who? Or medium according to who? So somebody had to take this number, 164 parts per million, and then determine that that was in fact medium. And that has to be done based on research. And if we don't have research that strongly supports that, then we shouldn't have much confidence in those interpretations. Okay, so the 4 requirements for success for a soil testing program is to have good samples. That may seem obvious, but there definitely is some ways that you can sample that give you bad data. You need to use the right type of soil test. You need to make sure that there's good data behind that type of that research. And then you have to make sense of the numbers and decide how you're going to fertilize depending on what the soil test said. So let's talk about proper sampling first. You want to take 10 cores per representative area. So if you want to soil test a green, you want to take 10 samples from that green, from random locations. If you wanted to use one sample to represent all of your greens, you still only need 10 individual cores from each of your 18 greens, okay? So the number 10 is the number of cores that provides the best data. So you get those 10 cores together, you mix them up really well, and then you send them off to the lab for analysis. But before you do that, you have to ask yourself, how deep do we want to test? And usually a good answer would be, well, you want a soil sample to the depth of where the roots are. But as you know, root depth can fluctuate during the season. And in fact, what you want to do is pick a consistent depth and always sample to that depth. And I'm going to show you why here with this piece of data. So we went to a golf course putting green, and we took samples from 0 to 1 inch, or about 2.5 centimeters, 0 to 5 centimeters, and then 0 to 15 centimeters. And then we looked at the amount of phosphorus that was in those soil cores. So you can see that when we sampled from 0 to 2.5 centimeters, the Mehlich-3 phosphorus content was about 200 parts per million. And in the exact same soil, if we just push the probe down deeper to 15 centimeters, the number dropped to 74. So that means that how deep you soil sample will influence the number that you get back from the lab. So I've had golf course superintendents call me up and say, look, we've haven't put phosphorus down for many years, but our soil phosphorus numbers just jumped up. And they're wondering why that happened. And the answer is likely that they took a shallower depth of soil from that last time that they tested. So to get the most consistent numbers, you want to pick a depth and be very consistent. Now, what is the right depth? For guidelines that we use here in Wisconsin, we say about 15 centimeters for our fairways and athletic fields and general turf. But for golf greens and tees, we're mowing our grass shorter. It's likely shallower root zone, maybe 10 centimeters. So I think the number the depth isn't quite as important as just being consistent. So if you decide to test at 10 centimeters, draw a line on your soil test probe and always take 10 centimeter deep samples. That's probably the most important thing you can do to get a good set of numbers. Okay, then you pick the right type of extraction. There's lots of different soil tests, and they work in different situations. So in Wisconsin, we use a test called the Bray, which is ideal for our slightly acidic soils. I'm going to talk a lot about the Mehlich-3, which I think is a very good test for turfgrass areas from different regions of the world. My guess is, I don't know the soil, I haven't seen the soil pH map of Spain, but I would guess that you have a lot of high pH soils, and the Olsen test is very good for high pH soils, as well as ammonium acetate buffered to pH 8.2. And then the soils that work for both high and low pH, the Mehlich-3 is one of those. So that's one of the reasons that I like the Mehlich-3, and I know that it's probably not as easy to find in Europe as it is here in North America, but I think it is a good test with a growing set of data behind it. So make sure that you match up the soil. The high pH soil, the Olsen is a pretty good test for you. And there may be others in Europe that I'm just not familiar with, but you want to make sure that that test is in fact okay for your soil. Now, this is the most important part, proper calibration. And that means that somebody has to do research to understand what those numbers mean so that we can assign a high, medium, and low value to them. It's expensive and it takes a lot of time, and therefore we just don't have as much data as we'd like to have. So that's what O.J. Knorr was referring to here when he said that we have imperfect methods and a lack of definite correlation with field experience. So I'm going to cross out the part that's underlined here, imperfect methods. I'd say that our methods are as good as they're going to get. We haven't had a new soil test developed since the 1980s. So since the 1920s, we have developed good methods, but this red portion, lack of a definite correlation with field experience, is still really important. So let me tell you why that's still relevant. So this is what soil testing calibration data look like. You have some response. In this case, we're using bushels of corn per acre, or amount of corn per acre, versus the amount of potassium in the soil. So you can see that this data is showing as we increase the amount of potassium in the soil, we get more and more corn. So farmers then know the price of potassium and they know how much corn is selling for. So they can do some basic math and figure out the ideal amount of potassium to apply to get the maximum economic value from that production. Now, unfortunately, we don't get to sell our clippings. So our response is usually visual quality. Okay, so from this curve, we can say there's low, medium, or high amount of potassium in the soil, and that's based on the economic estimated economic return. If you have low potassium, that means that there is a high chance that by adding phosphorus, you're going to make, or potassium in this case, you're going to make your money back. If your soil test tells you you have high potassium, that means that there is a very low chance that if you add potassium, that application would result in an economic benefit. And medium means, well, maybe it's close to 50-50. So you can do this. The graph here is for potassium, but you can do it for phosphorus and calcium and magnesium and pH. Anything that you can measure in the soil, you can develop a calibration curve like this. Now, the trick is that they're specific for the crop type, in this case corn, and the type of soil. So maybe this was done on a silt loam soil. These results might not translate to a sandy soil. So you'd have to do this experiment with corn again on a sandy soil or a clayey soil. So that's why it's expensive and time consuming, is because the data aren't universal across all different soil types. So we don't measure turfgrass yield very commonly. So our response factor is often quality, how good the grass looks. So here's an example of a soil test calibration study I did that looked at different levels of phosphorus in the soil from the Mehlich 3 test, and then how the bentgrass quality responded. This is A4 creeping bentgrass, and these plots here in the bottom that are turning purple, that's a classic sign of phosphorus deficiency, have about 3 or 4 parts per million Mehlich 3 phosphorus. These plots here that are starting to show signs of severe deficiency have about 5 parts per million. And then the grass right in the middle there, which is some of the best looking grass on the whole plot, had 7 parts per million Mehlich 3 phosphorus. So we go from 5 parts per million, where the grass is purple, to 7 parts per million, where it's very beautiful. Now we went up to as high as 17 parts per million, and the grass doesn't look any better than it does at 7. So phosphorus works sort of like a light switch. If you don't have enough, it's dark, the grass is bad. If you do have enough, the grass looks fine. And adding more doesn't make any more sense. That's very different than how nitrogen works. The more and more nitrogen you add, the greener and greener the grass gets. But that's not the case for phosphorus. So just put all the numbers up here. When it's a phosphorus deficiency is very easy to correct, and you just need to add some phosphorus. And this little stream of green that you can see cutting through this phosphorus deficient plot was induced just by a few drips from the sprayer. So we had a leaky sprayer. The student walked across the plots, and the drips from the sprayer that had phosphorus in it were enough to green up the turf grass there. So it's a very easy deficiency to correct with additions of phosphorus. Okay, another way that we can look at determining high, medium, and low values is to look at the amount of potassium in the tissue in the leaves of the turf grass and compare that to the amount of potassium in the soil. So if you look in a textbook, they might tell you that you want to have more than 1.5% potassium in the leaf. And so we would be looking for a soil test level that gives us more than 1.5% potassium in the leaf. So every single data point here was a soil sample and a tissue sample that were taken from a certain location. So I think there's over 100 or 200 different sites here, and each dot represents an individual sample from a golf course or a lawn. And if the soil test predicted the amount of potassium in the tissue, you'd expect to see a line that would start out here near 0 and go straight up towards the top. But we don't see that. We see sort of a cloud of data points that move uniformly across. So that means that I can have between 1.5% and 3% potassium at a very low level of soil potassium, or I could have either 1.5% or 3% potassium in the leaf at a very high level. So what it's telling us is that this soil test value is not very predictive of the amount of potassium that we see in the leaf, which tells us the soil test isn't working very well. And what our soil testing lab just drew a line at 50 at Wisconsin here and says this is the line between low and medium. And so if you're less than 50 parts per million, your soil test will tell you you're low. But what this research is suggesting is that even if your soil test level is low, there's a very, very high percent of chance that your grass has more potassium in the tissue than the commonly cited sufficiency level of 1.5%. Okay, so let's talk about potassium here. It's something I've been studying quite a bit here over the last 10 years at Wisconsin. It's often associated with rooting and cold tolerance and drought tolerance and wear tolerance and disease susceptibility. But I think it's important to look at the research behind all those, I guess, commonly held beliefs. So this is a great study that shows how phosphorus and potassium affect root growth. And the grass plant on the left here was exposed to low levels of phosphate at the top, high levels in the medium of the root, and low levels at the bottom. Same as the potassium. The root on the right had low potassium at the top, high potassium in the middle, and low potassium in the bottom. And you can see that the roots are really growing strongly in response to phosphorus, but not so much in response to potassium. So I don't think there's a lot of evidence that adding potassium is going to greatly expand the root system of a grass plant. At least in the United States, wear tolerance is usually thought of as the most important reason to apply potassium. But if you look at the research studies that have been done, there's really only one study that shows a clear benefit in terms of wear tolerance. That was done in the 1970s on bent grass. But in every single decade since, people have tried to replicate that result and have not found it. So here in another study in the 70s on bent grass saw no improvement to wear tolerance. Bermuda grass in the 80s, bent grass and bluegrass in the 90s, seashore paspalum in 2001, and perennial ryegrass in 2010. All those studies showed no benefit in terms of wear tolerance to potassium fertilization. So I would guess that it has less to do with wear tolerance than we often think. It appears that there's some good evidence that potassium fertilization improves the cold tolerance of Bermuda grass and centipede grass, another warm season grass. There's some evidence that it helps the cold tolerance of annual bluegrass, but then there's some studies that show no effect on tall fescue or perennial ryegrass. Here's the data from Rutgers on annual bluegrass. These plots here that are circled in black have the greatest amount of winter kill, and they also had no potassium addition. So the areas where the grasses are surviving had potassium added. So I think, again, if you have annual bluegrass and you want to keep it alive over the winter, that's likely not the case for most of the people viewing this, but adding potassium would be a good strategy. Drought tolerance, there's definitely some positive research results that show you can delay wilting or get faster recovery from drought by adding potassium fertilizer, and only one study that showed no effect in terms of drought tolerance to potassium. So I think the evidence show that cold tolerance and drought tolerance is an important function of potassium. But when it comes to disease, in terms of, and this is a snow mold, that the microdochium patch that happens in cool, cold weather, we see that the potassium additions actually makes the snow mold worse. So these are some similar pictures from my plots in in Madison. The plot on the left has had potassium added for 7 years in a row. The plot on the right has no potassium added, or it has sorry, I said that backwards. The plot on the left here has no potassium for 7 years. The plot on the right has a small amount of potassium applied for 7 years. And you can see the patches here of disease are bigger and more extensive than on the left. Same plot here, the next summer or the next winter, 2017, you see there definitely is some snow mold occurring on this plot that hasn't received potassium in 7 years, but the one on the right is more severely affected. No differences in the summer. So we get summer diseases like brown patch and dollar spot, and we don't see differences in those diseases. And in fact, you may expect if you don't add potassium for 7 years that the grass may start to look less vigorous or unhealthy, but that's definitely not the case. So the plot on the left here looks every bit as good as the plot on the right. So we start to wonder, like, what is the benefit of adding potassium to this bent grass, and where is the potassium coming from? So we studied the amount of potassium in the soil over that study period, and I apologize if this graph is a little difficult to see, but we definitely noticed a declining amount of potassium in the plots where we weren't adding it. Okay, so that green line is trending downwards over the year 1, year 2, 3, 4, 5, 6 years of data shown on this graph. But when we did some calculations to see how fast that potassium should be decreasing, we saw that we expected it to, or it was decreasing at about 1.5 parts per million per year. But when we calculated the amount of potassium that we were removing by collecting the clippings, we expected that should be decreasing by 46 parts per million every year, which is 30 times a bigger of a decrease than we were actually seeing. So the potassium is being removed, but it wasn't decreasing as fast as we would have expected by looking at the clipping removal. So this graph didn't make any sense. And we started wondering, where is the K coming from? Where is the potassium coming from? Where aren't these plots running out of potassium? So it turns out that potassium is a natural, is found in minerals naturally. And in fact, a lot of pink colored minerals, so if you look at your sand and there's a pink coloration to it, chances are that might be potassium feldspar. And also in a lot of the black minerals here, the micas, contain potassium and iron and other elements. So we looked at the amount of potassium in sands from all over the US, and I would guess that if you went all over Europe and all over Spain, you'd start to see a lot of different colored sands, and the color comes from the different types of minerals that make up those sands. So then we looked at the amount of potassium, the total amount of potassium in all these samples that were sent to us. Our study here is the one in yellow, so it had about 0.7 parts per million, or I'm sorry, 0.7% potassium. And most of the samples that we collected from all over the US had the same or more potassium than that. Only a few of them had less than 7% potassium. So we think that the potassium that the grasses are getting is actually coming from the soil particles, not the potassium on the exchange sites, but the actual particles themselves. If you look at the data of researchers that have studied the response of grasses to, or this is bent grass, the response of bent grass to potassium additions, you see a couple trends. When they use pure quartz sand, which is just like glass beads, it has no potassium in it, they see an improvement in the bent grass. One study that was done on a silt loam, and silt loams generally don't have a lot of potassium minerals in them, they saw an improvement in the visual response. But if you look at this group of green studies here that were done on putting green sands or just normal sands, not quartz sands, or sandy loams, you see no effect. And so that this is suggesting that that grasses grown in sands that contain potassium are obtaining the potassium from the individual particles of soil themselves, not from the fertilizer that you're adding or the potassium on the cation exchange sites. If we look at the Mehlich-3 soil potassium over time, we see the numbers sort of bounce around. These are from the study. The control plots have had no potassium added, and you can see it's decreasing, but it's not decreasing very rapidly, suggesting that the potassium in the soil is releasing and becoming made available to those plants. If we just look at the two plots here, the one that has a low rate of potassium addition, so in the English units, it's 1/10 of a pound per 1,000 square feet every other week. And that comes out to about 50 kilograms per hectare or 5 grams per square meter for the year. You can see it's hard to tell the difference in terms of the amount of potassium in the soil between the plot that's fertilized every year with that amount or the control. So they were statistically similar on 2/3 of the testing date. But if we look at the amount of potassium in the tissue of the plant, we see that they are statistically similar only 30% of the time. And in fact, these lines never cross. So we always found more potassium in the tissue from the plot that received small additions. So this suggests that maybe tissue testing is a little bit more useful than soil testing, and than soil testing. So let's talk a little bit about tissue testing. How do you want to test your tissue for nutrients? First, collect a representative sample of clippings from the area of interest. Now, we talked about to do that for soil, you take 10 cores from that area. For clippings, I would say, mow the area with a clipping collection basket, and then mix them up with your hand, and then grab a sample. Make sure that sample that you grab out is free of any sand or leaves or other debris, because that will mess up the lab analysis. Don't collect the clippings shortly after a fertilizer application. The fertilizer obviously will greatly exaggerate the lab results in terms of the nutrients. If you have an oven, and you can dry them at about 50 degrees Celsius for 24 hours, that's ideal. But most people don't have access to an oven. So the next best thing is to spread the clippings out on newspaper overnight. Make sure you do this in an area that's not going to be exposed to wind, because as soon as the clippings dry, the wind will just blow them everywhere. So usually letting them dry overnight for 24 hours will be dry enough that you can put them in a bag and then send them off to a lab. If you send the clippings to the lab when they're wet, they'll start to ferment and rot, and the results you get will not be as reliable. Okay, so how do you interpret those nutrient ranges? Again, we don't have really a lot of very solid data that tells us how to interpret these numbers. And if you look in textbooks or other publications, you might find general ranges like for nitrogen, you want it to be between 2 3/4% and 3.5%, or for iron between 50 and 500 parts per million. And so those are just general guidelines that may or may not be accurate for your particular situation. There are macronutrients, the nitrogen, the phosphorus, and the potassium, that are most commonly deficient. And then we also can test for secondary macronutrients like calcium, magnesium, and sulfur, which are very, very rarely deficient. And then the other group here is the micronutrients, which are found in very small quantities in the plant. And I would say our data for interpreting these ranges is very questionable, because again, deficiencies are so rare. So we probably have the best information on the primary macronutrients, the nitrogen, the phosphorus, and the potassium. Now, I know that many in the audience are growing warm season grasses. So this is a set of ranges from the University of Florida. Travis Shaddix compiled these when he was there. Again, for Bermuda grass, this is a really wide range, between 2.3 and 5% nitrogen. Seashore paspalum, 2.8 to 3.5. Zoysia grass, 2 to 2.3. So you can see there is a definite range depending on the species that you're growing. So I don't want to say that tissue testing is a extremely valuable practice that everybody should do. I think it can be useful in some cases, but this last bullet point here, don't chase numbers. We're not very confident in the research that we have to the point where you should be basing your fertilization program off of your research or your tissue results. I think a better strategy is to use tissue testing to develop an understanding of how your numbers trend over time. Are they going up over time? Are they going down over time? Are they fluctuating seasonally? How stable are those values? After you do that for a number of years, a number of seasons, I think you can start to understand what a healthy range for your course may be based on what you're seeing. So again, use the numbers to develop an idea of what's acceptable for your club or your practice, but don't follow the guidelines and try to adjust your fertilization program to chase numbers. Now, I did say we don't have a lot of good information on what tissue testing ranges are right, but sometimes we do. We have studies that are done occasionally that give us these kind of useful snapshots. Now, again, I don't think a lot of people are worried about annual bluegrass cold tolerance in the audience here, but these are the types of studies that you want to pay attention to when they're done for your particular situation. So in this case, Katie Dodson up in Canada identified the optimal ranges of nitrogen and potassium in annual bluegrass that produced optimal cold tolerance. Okay, so you can read about her study there, and then if this is your situation, maybe you could use these numbers as a guideline or to help you understand how you may be doing for cold tolerance. But until we have more data on all the different scenarios for seashore paspalum and bentgrass and Bermuda grass, I think you need to take these numbers that the soil testing lab will give you with some skepticism. These are the data that we've done for bentgrass on potassium. So I'm sure we have some bentgrass managers in the audience, and we think that keeping your potassium levels at or above 1.5% in the summer is a safe spot to be, although we've seen good bentgrass grown as low as 1%. In Wisconsin here, we think that you're better off allowing your potassium levels to drop as the temperatures get colder, and that's because it gives you tolerance to snow mold diseases. And then based on our research, we're suggesting that if you have more than 0.7% total potassium in your sand, you may never need to apply potassium because that your bentgrass is obtaining that potassium from the sand itself. Now that is a very, very specific recommendation that applies to bentgrass grown on a sand. This doesn't translate to seashore paspalum, it doesn't translate to Bermuda grass, but as the research develops, these are some of the cool things that we can learn from our soil testing and tissue testing values. Similarly, for annual bluegrass, there's been research done at Rutgers that's shown that you want to keep your tissue levels above 2% all year. So again, if you go back and look at those general ranges, and Xavi's provided you the handout so you can use that as a reference guide, these numbers may not show up exactly on those ranges, but they're based on very specific research. So if you don't want a tissue test, which I think is fine, I'm not sure that tissue testing is right for everybody. I think you can focus on maintaining your soil levels near the MLSN guidelines. Now, we haven't talked specifically about what MLSN is. Essentially, it is a set of soil testing interpretation guidelines developed by Pace Turf and the Asian Turfgrass Center using a very large set of soil samples from sandy soils all over the world. And so those levels I have a good deal of confidence in. If you maintain your levels near those ranges, that you will not run into nutrient deficiencies. So you can download the MLSN, which is the minimum levels for sustainable nutrition guidelines. You can download that for free online, and maybe Xavi can provide that handout after the class. But again, it's for the Mehlich-3 test. So if your lab is not offering the Mehlich-3 test, those guidelines are not useful to you. So keep your soil levels near the guidelines that are research-based, and you should not really require tissue testing. Okay, the last thing I want to talk about here is how to make sense of the numbers. So assuming that you have done a good field sampling, you've taken your soil tests to a very particular depth and you haven't varied that, you're using the proper test, and that test is based on good data, interpreting the numbers is the next step. There's really two types of philosophies. The first one is called the sufficiency level of available nutrients, or the SLAN approach, and then the other one is the base cation saturation ratio, or the BCSR. Most of the people in the world use the BCSR philosophy, and that's unfortunate because the university research and the university science says that there's not a lot of evidence that works, and that you should use this more simple approach, the SLAN approach. And the MLSN is within the family of the SLAN approach, and I think I'll show you what I mean in a second here. But let's talk about why university scientists have almost universally agree that the base cation saturation ratio is not a good test to use. This idea holds that there are ideal ratios of the cations, and the cations are calcium and magnesium and potassium and sodium, and it relies on the concept of the cation exchange capacity. So your soil has these negatively charged sites, and those negative charges attract these positively charged cations, as you can see in the picture. The BCSR concept says that you should have between 65 and 85% calcium on those exchange sites, 6 to 12% magnesium, and 2 to 5% potassium, and the rest will be either hydrogen or ammonium. And so the agricultural research that's been done suggests that this technique does not work. Okay, so in corn, soybeans, wheat, alfalfa rotations, researchers have found very low correlation between the soil levels, the BCSR levels, and yield. And they actually found that if they took the 5 greatest corn yields and the 5 lowest corn yields, that the base cation saturation ratios were similar. So their conclusions were that there is no evidence to suggest that using the BCSR will maximize crop yields. Now, of course, we're not trying to maximize yield. We're trying to grow healthy grass. At Iowa State University, researchers looked at how bentgrass responded to these different ranges of calcium, magnesium, and potassium in the plant. And in order to be considered ideal, your test would have to be in the small range here of these blue dots. And these red dots were all the other ranges that the researchers used to grow bentgrass. Okay, so you can see that they grew grasses in a wide variety of conditions, and they found no difference in the turf quality or the clipping weights across all these different ranges. And so their conclusion was that creeping bentgrass, or Grassus stolonifera, can tolerate wide ranges of cation saturation in the soil. So again, no evidence that using this base cation saturation philosophy is working. Now that actually makes sense based on what we know about how plants work. If a plant is low in calcium, it'll actually build proteins on the outsides of its roots that will increase the absorption of calcium. And if it has a lot of calcium in the root zone, it will tear down those proteins and then build new proteins that maybe take up something it's deficient in. So your plant is reacting to the type of soil that it's growing in. And so you don't need to worry about balancing and getting just the right amount of nutrients in the soil. The plant can take care of that for itself. So my conclusion is to avoid any approach that's using a percentage based interpretation or a cation balancing interpretation. And in fact, you want to compare your results to this article here, I think, which was published back in 2004 by Bob Caro and other scientists, which talk about a whole wide range of soil extractions and what the probably best ranges are for you to follow. But this is what the MLSN, again, the minimum levels for sustainable nutrition soil guidelines look like. Again, you can download this for free, and it tells you the optimum ranges for potassium and phosphorus and calcium and magnesium, etc. So again, I think this is probably the best set of soil testing guidelines that we have. But unfortunately, it's limited to just the Mehlich 3. I believe the subsequent versions have eliminated the Bray and the Olson results. Although you could still use this screenshot here to say that, you know, if you're using the Olson test, you should keep your phosphorus level above 6 parts per million. Okay, but again, you know, this drives home the point of how important it is to know what the soil test extraction you're using is. So optimum for the Olson might be 6, but if it's Mehlich 3, it might be 18, or if it's the Bray 2, it's 25. So it's hard to interpret these numbers without knowing exactly what type of soil extraction is being done. So I'd encourage you, if you don't know that, to go find out what that test is so you can use the most proper interpretation guidelines. Okay, so I'm going to wrap up today with a case study about how soil testing can go wrong. I see more people use soil testing, which is supposed to be done to save money and to decrease unnecessary applications. But in my experience, I see people use soil testing and end up spending a whole bunch of money on fertilizers and making applications that probably aren't used. In fact, probably the best approach for managing turf sustainably is to not test your soil and to not tissue test. Just use your eyes, and if you have a problem, soil and plant analysis might be a good step for you to use. But if your greens look good, like in this case here, chasing soil and plant tissue levels can actually end up costing you a lot of money. So in this case, soil cores were taken from 3 greens, analyzed by a very reputable lab, and interpreted by a fertilizer company, which is very common. The fertilizer companies like soil testing because it helps them justify the products that they're selling. This was the interpretations were 11 pages long and very complex, but these are the summary. Basically, everything that soil test was looking at was found to be low. Organic matter, calcium, in this case they said calcium was high if it was exchangeable, but the soluble calcium was low. Magnesium low, potassium, zinc, manganese, cobalt, copper, iron, everything was low on this test, but the grass looked great, right? So that is a suggestion right off the bat that those interpretations, they're saying low, you should be asking according to who? Where is the research that says that this number is actually low? The grass looks good. That means actually that those numbers are acceptable for your golf course. And then you could continue testing year after year, and as long as those numbers were there, you would know that you don't have a problem. But anyway, let's take a look at these interpretations in a little more detail. They said the exchangeable percent calcium saturation. So when you see these words, saturation of calcium, that's your clue that they're using the base cation saturation ratio, and that you should be not following these recommendations. Now this one's interesting because they say your exchangeable calcium is too high, but then on their bullet point, they tell us that the calcium availability is low, and this just doesn't make any sense to me. If your exchangeable calcium is high, it's likely that your plant has access to more than enough potassium. So I'm not sure why their recommendation said that. They also said your soluble calcium was too low and that the calcium reserves in the plant were inadequate. Again, I don't understand how you can have exchangeable calcium that's too high and soluble calcium that's too low. Those two things are actually connected in this way. So calcium ions are on the exchange sites, and the amount of calcium in the soil solution, in the soil water, is directly related to the amount on the exchange sites. So to say that your calcium and soluble calcium is too low and your exchangeable calcium is too high just doesn't make any sense. So anyway, again, a lot of soil testing can be very complicated and intimidating, and sometimes that's done on purpose to make you think that, well, you need to buy these products to solve these complicated problems. And my advice is don't do that. Okay, so let's take a look at why this recommendation here is really bad. So in this case, they recommended a liquid calcium chelate. The product was 8% calcium, and the instructions were to apply it at 6 ounces per 1,000 square feet. If we assume 1 gallon weighs 10 pounds and 6 ounces per 1,000 square feet, we can calculate that out to be about a half a pound of product per 1,000 square feet. Now that comes out to be about 25 kilograms per hectare, or 2.5 grams per square meter. If we take that half a pound of product, or 25 kilograms of product per hectare, and we multiply it by 8% to figure out how much calcium we're applying, we get a really low number, 0.04 pounds of calcium per 1,000 square feet. Okay, so that is just really small amount of calcium. If we look at the amount of calcium in this irrigation water, and my guess, if your soil pH is high, you likely have high calcium in your irrigation water. In this case, it was 70 milligrams per liter. The golf course superintendent would maybe apply about 1/10 of an inch, or about 2 millimeters of water to 3 millimeters of water to water in an application. That's about 236 liters per 1,000 square feet. Turns out that amount of water has the same amount of calcium in it as the product. So the product had 0.04 pounds per 1,000 square feet of calcium, and just a tiny amount of water, irrigation water, had that same amount. Okay, so this is why that recommendation doesn't make any sense. Number one, the assumptions about the calcium in the soil didn't make sense. The product that was recommended put down a very small amount of calcium. If you truly had a calcium deficiency, you should be going out with 50 kilograms per hectare, not 0.0, not a fraction of that, not 0.05 kilograms per hectare. So in summary, and this was a real life example, it happened just at a golf course just outside of where I live. Applying a product at the labeled rate resulted in the same amount of calcium as 3 millimeters of irrigation. If the superintendent applied that product according to the label directions, he would apply about 0.08 pounds of calcium per 1,000 square feet. And if that golf course superintendent irrigated normally, normal irrigation for Wisconsin in the summer, he would have applied 10 times more calcium just in the irrigation water alone. Okay, so in summary, this is something that we see a lot of times. People who soil test and tissue test and chase numbers end up spending more money and more product and more labor when their grass looks really good and healthy. So I'm gonna conclude on this slide, and then hopefully open it up to questions and comments. But I think soil and tissue testing is it can be valuable if you use those numbers to see how they're changing over time. I'm not very confident in our ability to say what low means, what high means, what optimum means, because we just don't have enough research. But if you track how your golf course is responding and what those tissue levels do over time, I think you can start to learn things. So eventually you'll see these patterns develop that you might be able to respond to. If you're chasing numbers, and by that I mean if your soil test says you're low, you go right out and apply the thing that you're low in to try to get that soil to say medium. I think you're wasting your money, you're wasting your time, and which could be better spent on improving drainage or dealing with other issues, traffic issues on your course or shade issues on your course. So again, one of the mistakes I think I see people make is putting too much value on soil and tissue tests. So we'll go right back to that quote that we started this seminar off with. There's a tendency for people to put too much emphasis on the value of soil testing. And it's true of scientists, and it's true of salesmen, and it's true of golf course superintendents. There is some value to it, but until we have much more and better data, you shouldn't be chasing those numbers. Use it to track your values. Don't use it to chase numbers. And with that, I would like to thank Xavi very much for the invitation to speak with you all today. Thank you so much to the sponsors for making this possible, and I would be happy to open it up for questions or comments at this time.
Hi, Joe. Not thanks to you, sincerely. First of all, just one consideration. Under my point of view as a golf course superintendent, I want to say thanks to you and other several researchers like Larry Stowell, Michael Boots, or William Cruiser. Like, I think that you are providing such amount of common sense and a very profitable knowledge and information about your management that it's incredible. So thank you.
Oh, thank you. That's very kind.
No, yes, I absolutely agree with all your research. And then there are several questions. The first one about the percentage of potassium in the leaves. It is very specific. The amount of potassium and the leaves are like 1.5 or 2.0 in bent grass, but which would be the management on mixed bent poor greens?
Right. I mean, and that's where I say don't chase numbers, because situations like that make knowing, you'd have to have a pretty good estimate of the percentages of bent and POA, and then you have different greens that might have different compositions. It makes it really difficult. So I think, if you're trying to keep the annual bluegrass alive, you would try to get everything up above the 2% range, right? To err on the side of caution. But I think it's bad to use that tissue test to dictate your fertilization event, if that makes sense. So my recommendation would be to maybe target your fertilizer applications near those periods of stress. So for example, annual bluegrass, one of the reasons we like to keep it elevated in potassium is to minimize anthracnose. And so anthracnose happens in the summer stress period. So apply the potassium every other week in small doses all throughout that stress period. And that's going to elevate the potassium status of the plant. You don't have to know what the number is, but your fertilization is going out to feed the plant, right? Or the other time we like to apply potassium to keep it alive is for cold stress. And so you would time your application near the late fall when the winter's coming. So again, I'm not really confident that we can use those specific numbers to know for sure what that right number is, but it can teach us something about how you might want to plan your applications.
Okay, thank you. Another question. I just, by the way, I send you the question. You have on your chat box. You have your question. Just if you want to check in. I'm gonna read the questions for the audience. So the first one is from Jose Angel Sanchez Alcalá. He's a golf course superintendent from Spain. He is asking, taking into account the results with different nutrients, mainly potassium, has the microbial flora of the soil been taken into account? and the way in which the nutrients have been applied, and how could this affect this microbial flora?
Yeah, really good question. And for how little we know about what the soil and tissue levels are in grass, we know even less about how those levels and applications affect the soil microbes. And this is the area of research in soil science that is the most exciting right now. Is we're starting to figure out that these microbial associations make a lot of difference. And we have some evidence that so mycorrhizae are these fungi that infect the plant, but they benefit the plant. They provide water and phosphorus, and you're less likely to have these mycorrhizal infections if you add too much phosphorus. So that's one example that we know, like your microbial benefits will go away if you over apply certain nutrients. But there's millions and millions of different microbes that live in the soil, and we just don't know that much about them. It's really exciting, but we're still learning. So it's a good question that likely has an answer that we just don't know yet.
Okay, the second one from Jose Angel. Have you carried out studies taking into account the use of silicon and glycine and beta in amino acids?
I haven't specifically done studies on those three products. So I've read a lot of work on silicon. It seems like the public perception of silicon is that it helps with wear tolerance, but there's almost no evidence that that's the case. There is some evidence that it helps with manage or decrease the incidence of certain diseases. And so if I had those diseases and I was looking to minimize my pesticide inputs, or I didn't have the budget or the means to control it, I would look into that. Glycine and betanine amino acids. So I guess we have applied fertilizer trials that fertilizers contained amino acids, and we have never seen a direct benefit over a similar amount of nitrogen applied in the form of urea. There's good theoretical reasons to imagine why applying nitrogen in the form of amino acid might make sense, because the plant takes up the nitrogen and then it builds amino acids. So if we just gave the plant the amino acids, maybe that would be better. It makes sense in theory, but again, I haven't seen direct benefits in practice. Those amino acids contain carbon, and they may stimulate microorganismal activity, like I just said, might have an impact. But we know so little about the soil biology right now that it's hard to make recommendations. I encourage superintendents to experiment and play around, and I think that's one of the ways that helps us researchers get better, is by learning from your observations.
Okay, thanks. Just one thing about to the attendees. You are welcome to use your micro to ask any question. So if there is anyone interested in using the micro, just ask. There is another one question from Raul Bragado. He's another golf course superintendent from Spain. Good evening. I use soil paste analysis to know about soil salinity. But then, using those data, I have realized that soil samples which are saturated on minerals like calcium carbonate are the highest on calcium leaf tissue, while while those unsaturated are the lowest on calcium leaf tissue. Sorry, no, I'm lost. Oh, okay.
Yeah.
What do you think about it? Does it make any sense to you? The soil with low calcium tissue had saturation indexes below 0.5, and those with high calcium tissue had saturation indexes above 0.5.
Right. Yeah. Okay. So the saturated paste extract is excellent for pH and salinity. I think it's unfortunate that we pay attention to the other things in there, like the phosphorus and the potassium and the calcium, because those amounts, of even the calcium that is you're saying it is varying in that solution. It absolutely varies, but it's such a small amount relative to the amount that's on the exchange sites that it's not we haven't seen the evidence that that's predictive of turfgrass response. So I would suggest ignore it, even though you're seeing trends in there, and those trends are starting to make sense or make a pattern to you. The patterns that we see are much stronger when you use when you measure the exchangeable ions. Okay, so again, but I think you're doing the right thing, right? So you're paying attention to your grass, and then you're looking at these numbers. Okay, so if your grass looks good in both of those ranges, at the above 0.5 and below 0.5, then it should mean that maybe this doesn't make much sense to care about. But if you're noticing that all my greens that have these low saturated values are bad, and the greens that have the high ones are good, that's how you should use it. But don't just chase the number because they say you should be at 0.7 or 80% saturation. But look at the numbers, look at the trends, and then see for yourself. My guess is that you're going to notice high performing greens at high and low saturation values, and it doesn't matter. But I like your approach.
Okay, thank you. Another question from Jose Ron. He's a superintendent from Uruguay. He's asking about if you have any experience on winter kill tolerance on Bermuda grass with potassium.
Yeah, I don't. Unfortunately, I live in a part of the U.S. where it is too cold to grow Bermuda grass. But like I said, there are some studies that have been done that shows low levels of potassium in Bermuda grass will show increased winter kill. So I think there's definitely something to that, and that tells me that I would target my potassium applications toward that the period where the Bermuda grass is hardening. The question is, what is this appropriate soil level? So there's likely some soil level that's high enough where you don't have to apply potassium to see that benefit. But again, that's the type of research that there's just not enough of where I can say, yes, go to this paper and this will tell you exactly what level to hit. So my thing is use the research and the concepts of soil testing to guide your management. Don't use it to chase numbers.
Okay, great. Another question, this is from Bernardo Almeida. He's a golf course superintendent from Portugal. You have the question in your chat box if you want to check it, because it's a little bit long. So the question is, hello, to increase pH in a sand soil with low organic matter and a pH of 4.5, which is the best way? 1,000 kilograms per hectare per year with calcium carbonate. 60 to 70% calcium concentration. Avoiding fertilizer with sulfate, is it important?
Right, that's a good question. So based on the grasses that I grow and the research I've seen, you probably want to keep your pH at least at 5.5. And the reason we say that is because there's a lot of soil microorganisms that stop working below that pH, and you may get thatch accumulation or organic matter accumulation, or your nitrogen use efficiency will drop. So I think for most grasses, a target pH of 5.5 is good, and you can get there by applying calcium carbonate like you suggest. And you should get a soil test done. This is one very reliable aspect of soil testing, is the lime requirement. Send your soil test into a lab, tell them that you want a lime recommendation. They should ask you, what's your target pH? And I think you should say at least 5.5. And then they'll run some tests to tell you how much calcium carbonate to add, because it's going to be different on a sandy soil than clay soil, or a soil with low organic matter or high organic matter. So send that off to the lab, and their number should be pretty good. The only thing you'll have to think about is you have established turf, and they might tell you need, let's say, 200 kilograms per hectare of calcium carbonate, but you don't want to put that down all at once. You're going to have to split that up into safe applications, and usually you don't want to exceed more than 50 kilograms per hectare. at any one application. So it might take you 4 or 5 separate applications to hit that target recommendation, but just absolutely use the soil test recommendation to determine how much lime to add. Good question.
Okay, and the last one from Bernardo. What's your opinion about fertilizing just with foliar-insoluble fertilizers?
Yeah. Oh, and you know what? I realized I didn't answer the sulfate question. I think maybe the genesis of that question is if you use a sulfate that you're going to lower your pH, but the thing that does the acidification is actually the ammonium. So ammonium sulfate is very acidifying, and something like aluminum sulfate is very acidifying, but it's not, and sulfur is acidifying, but sulfates is not. That said, I would probably avoid ammonium sulfate because ammonium sulfate is is more acidifying than other products. You can switch to urea, which is also acidifying but less so. Or a neutral fertilizer would be something like potassium nitrate. But in general, just use your calcium carbonate to get your pH in the right value. You shouldn't have to worry too much about the form of fertilizer you use. Now, the second question was, what do you think about only foliar and soluble fertilizers? I'm a big fan of that. I don't think that there is a huge need to go with granular fertilizers all the time. They're useful when you want to put down relatively large applications, but in my experience, my philosophy has been to use spoon feeding. So usually, I mean, my specific program is urea because it's very, very soluble and it's very good at being foliar absorbed, and to use potassium sulfate that's soluble, and even soluble forms of phosphorus. And if you apply those every other week, you can get very good control over your fertility. So if the grass looks green, you don't have to apply. If the grass looks hungry, you can double the amount that you might put down. So I like soluble and foliar fertilizers because it gives you a lot of control. But there's not anything inherently wrong with using a granular fertilizer as well.
Okay, thank you, Jock. This was the last question. Just let me say that I appreciate very much your time and your collaboration with Campus del Césped again, and you are always welcome.
Great, I'm happy to participate. So thanks for your attention today, and have a good season.
Sorry?
I said have a good season. Have a good.
Let's hope.
Yeah, let's hope.
Okay, thank you very much. Just let me say goodbye to the in Spanish, and so thank you. Bueno, pues hasta aquí las preguntas, o sea que ya damos por concluida el webinar de hoy. Bueno, pues como siempre agradecemos la colaboración de nuestros patrocinadores y ahora tenemos el próximo webinar. Al principio estaba programado para el 29 de abril, pero el ponente me ha pedido un cambio de las fechas, o sea que estaremos al tanto de la nueva fecha. Mientras tanto, el día 8 de abril tenemos un webinar de Golf Management orientado a directores, pero también los Greenkeepers sois bienvenidos porque vamos a hablar de inversiones en los campos de golf, o sea que estamos también incluidos en el tema. Será interesante, pues estará ofertado por Carlos de Linares, es un director de golf que está ahora mismo en la República Dominicana, o sea que bueno, será muy interesante. Vale, pues por mi parte nada más. Muchas gracias a todos por vuestra asistencia y hasta la próxima. Thank you very much again, Doc.
Yeah, and thanks to Carlota. Appreciate it.
Yes, of course. She's great.
Yeah, absolutely.
Bye.
Thanks. See you later.
See you. Bye. Bueno, pues venga, hasta la próxima. Adiós.